Hello. So, welcome again to module 3 where we were discussing different numerical ways of solving linear equations. In the previous lectures of the modules we covered what is known as the direct method for solving the linear equations. The direct methods that we considered included Gauss elimination method, Gauss-Jordan method, the LU decomposition method, and we also covered basically a tridiagonal matrix algorithm which is specific to a special type of tridiagonal matrices. As opposed to this direct methods, the quality of the direct methods that we looked at essentially was that when you get set of equations and we solve these set of equations, provided we do not have any round off errors, the results that we are going to get are going to be exactly accurate. Okay, so that's and the reason why they are called direct methods is because once you get the solution, you have the solution. We don't iterate over the solution multiple number of times. As opposed to the direct method, there is another class of methods known as iterative methods. For solving linear equations, and we will basically be covering the iterative methods in this part of the lectures. Okay, so the examples of iterative method, the first example that we will start off with is known as the Gauss-Siedel method. Okay, and I will take a relatively simple example of two equations in two variables, and actually I will show you how the Gauss-Siedel method works. Under certain situations how the Gauss-Siedel method does not work, what we need to ensure in order to say that the Gauss-Siedel method we can get it to work, and we will look at essentially how to analyze the results that we get from the Gauss-Siedel method. So the simple example that we are going to talk about again is basically going to be x plus 2y let us say equal to 1 and x minus y equal to 4. So the solution for these two equations we know is 3 comma minus 1, that is the solution. Okay, and we can solve it in a fairly straightforward manner using Gauss elimination method. What we will see now is how to use the Gauss-Siedel method. What we do in Gauss-Siedel method is rearrange this equation so that we write it in terms of x equal to something to the right hand side. We rearrange this equation so that it becomes y equal to something to the right hand side. Okay, and two possible ways of rearranging this equation are fairly clear. So you can take 2y onto the other side and you can write x equal to 1 minus 2y, and the second equation you can write this as y equal to x minus 4y. Okay. So what we have done is we have used the first equation to express the overall result in terms of x. We have used the second equation in order to express the overall result in terms of y. So that is one way of rearranging these equations. The second way of rearranging these equations is to use this equation to obtain x. So we will write the second equation as x equal to 4 plus y, and the first equation we will write that as y equal to 1 minus x divided by 2. Okay. So the first step, as we have said, we have done nothing but just rearrange these equations such that we have the unknown variables to the left hand side and we have what we will for the time being considered as known variables to the right hand side. Now it is an iterative procedure, so what we will do is we will start with an initial guess. Okay, x superscript 0, y superscript 0 I represent superscript in the bracket in order to say this is the initial value, the 0 represents this is the initial value, and as we iterate multiple number of times, this particular coefficient will become x1 y1 x2 y2 x3 y3 so on and so forth. Okay. So we use these rearranged equations as an update equation in order to improve the value of x and y. So let us look at if we use the first equation. In that case we will write x I plus 1 equal to 1 minus 2y, the value at the ith equation, and then the second equation we will write this as y I plus 1 equal to x I plus 1 minus 4. Okay. So these are the two equations now we are going to use. Notice what we have done is in the equation for x we have used the previous value of yi. In the equation of y we have used the newest value of x. So what we do essentially in a Gauss-Seidel iteration is use the latest values of x and y that we have computed through the iterative process. Okay, and we will start with some value, and let us say we will, just for convenience sake, we will start with origin. Okay. So we start with origin and use these equations in order to find out the new solutions of x. So let us say now what happens at iteration number 1. Or rather I should say at I equal to 0, what we get is x1 equal to 1 minus 2 times y0, which means basically our x1 is going to be equal to 1, and we substitute that value 1 in this particular equation, and y1 we are going to get is 1 minus 4, that is equal to minus 3. Okay. And at this point of time what you can do is just try to basically solve these equations in order to get x2, x3, x4, x5 and so on, and we will keep doing that. So we will substitute the value y equal to minus 3 in this equation, so this becomes 1 plus 6, so x2 becomes 7, y2 when we substitute that value in this particular equation, y2 will get the value of 3. Okay. Now what we do is we iterate on this again, x3 is essentially going to be 1 minus 6, that will end up being minus 5, and essentially y3 will end up being minus 5 minus 4, that is going to be equal to minus 9. Okay. And we continue doing this over and over again, and we will find that this particular solution does not converge to the desired to the actual solution x equal to 3 and y equal to minus 1. So we keep on repeating the process, and we will find basically that x is going to go to minus infinity or plus infinity, and y is also going to go quickly diverge to plus or minus infinity. Okay. So that is what if we naively use equation the form 1 in that is this particular equation is recast in this form and this particular equation is recast in this form. Okay, I actually made an error over here, so we will have y equal to x minus 4 and not x minus 4y. Okay. So if this particular form is used, what we see is that we are not converging to the desired solution. Let us use the second form of this equation, and the second form essentially was x equal to 4 plus y and y was equal to 1 minus x divided by 2. We started off with x0 equal to 0, y0 equal to 0. Okay. So, we substitute y0 in this particular equation, we will get x1 equal to 4 plus 0, that is 4, y1 is going to be 1 minus 4, that is negative 3 divided by 2, that is minus 1.5. Okay. Then we substitute minus 1.5 in this equation, and x2 we will get x2 as nothing but 4 minus 1.5, that is 2.5, y2 is going to be nothing but 1 minus 2.5, that is minus 1.5 divided by 2, which is minus 0.75. x3, we continue this, we substitute y2 into this equation, that is 4 minus 0.75, we will end up getting this as 3.25, and y3 is going to be 1 minus 3.25, that is minus 2.25 divided by 2, that is minus 1.125, and we continue doing this until a long enough time, and we will get our solution of x3 equal to 3 and xn equal to 3 and yn equal to minus 1, where n we choose as large enough such that the results that we get we say are converge. So, what is the stopping criteria that we are going to use? The stopping criteria, keep in mind that essentially we do not know a priori what the solution is. For this particular example, yes, we do know that the solution is 3 comma minus 1, but in general we do not know what the actual solution is. So, what we have to do is we have to compare the solution xn with xn minus 1 divided by xn minus 1. This was our approximation error, and we do that for all of the variables, and if this value turns out to be less than some tolerance value that we specify, at that particular condition we say that our overall iterations have converged. For example, in this case x0 has changed from 0 to 4, that is a pretty large change that we observe. In this case it has changed from 4 to 2.5, so the change is actually 1.5 divided by 4, so that is a pretty large percentage of change, almost 35% change when you go from 4 to 2.5. Likewise, from 2.5 you are going to 3.25, that is also a pretty large change. After a certain point we will see that xn minus 1 and xn and so on and so forth, they will start differing from each other with relatively small amounts, and when that difference falls to below epsilon tolerance, at that time we say that the overall Gauss-Seidel iterations have converged. So, the question is when do we use in the methodology number 1 and when do we use the methodology number 2, and we will not prove this for now, but we will keep that proof for a later time. We will do that proof in perhaps in the third or fourth lecture in module 4 when we talk about nonlinear systems. But what is required to ensure that these equations converge, the Gauss-Seidel methods when we are applied on these equations will converge, is what is known as a diagonal dominance condition. Okay. What that means with diagonal dominance condition, so if we look at this particular equation and we put it in the form Ax equal to b, our matrix A, we can write this as 1 2 1 minus 1. Okay. Of these, again these elements are the diagonal elements. Now, if the absolute value of the diagonal elements is greater than the sum of the absolute values of all the elements in that same column, in that particular case we say that the diagonal dominance condition is met. So, the diagonal dominance condition is going to be the absolute value of A11 should be greater than or equal to summation from 2 to n A1I. Okay. In this particular case the absolute value of 1 is indeed greater than or equal to the sum of the absolute value of the non-diagonal elements. So for this particular condition this diagonal element is dominant when we are looking at the first column. Also A22 has to be greater than or equal to summation I equal to 1 to n I not equal to 2 A2I. Okay. In this case the absolute value of A22 is 1 and the absolute values of so now the absolute values in that particular column, if we actually look at this particular value is actually going to be equal to 2 and this condition is not met. So what we get with the matrix A is that the diagonal dominance condition is not met. In the case where the diagonal dominance condition is not met, we cannot guarantee the stability of the Gauss-Siedel iteration. So as we increase the number of iterations, the Gauss-Siedel iteration may not converge to the true value. However, if the diagonal dominance condition is met, that means instead of writing the equation in this form, we have swapped around this equation and we have written those equations in the form A bar is 1 minus 1, that is this row, and the second row is 1 2, and of course we have to change B bar also. Original B was 1 4, now that we have swapped these two equations the B bar is going to be 4 1. The solution of A bar x equal to B bar is the same as the solution of Ax equal to B. I will write down the B over here as well. Okay. Now in this condition, in this particular matrix form, what we actually get is indeed this is the largest value in this particular diagonal and this is all in this particular column, and this value is also the largest value in this particular column. When we have in general an n by n matrix, we have to consider basically that the diagonal element, the absolute value of it should be greater than the sum of absolute values in the entire column for each and every diagonal element. Okay. So we will draw our two axes x and y. Okay, and the other line is x minus y equal to 4. So that particular curve is perhaps going to be represented in this form, and we will just extend it beyond. Okay. So we will call this equation as x plus 2y equal to 1, and this particular equation is x minus y equal to 4. Okay. This point is essentially our x0 comma y0. Okay. So our first equation what we used was we used x1 equal to 1 minus 2y. X1 we said was equal to 1 minus 2y. Okay. Sorry, 1 minus 2y0. Okay. So what does 1 minus 2y0 represent? 1 minus 2y0 represents a point on this particular line. We are going to keep the same value y0, y0 is going to be 0. So we are moving along this line to represent y0. Okay, and we will reach essentially this particular point. This particular point is indeed 1 comma 0, that is because it satisfies the equation of this particular curve. So what we ended up doing is the first iterative step, we went from the point x0 y0 to the point x1 y0. So x1 is 1, y0 equal to 0. Okay. So this point is x1 comma y0. Okay. Then we used the second equation, so that we had y1 equal to x1 minus 4. Okay. Y1 equal to x1 minus 4, so we are keeping the same x1, so we are going along this line and we will essentially reach basically this particular line. Okay. And we have now reached this particular point is essentially x1 comma y1. Okay. Why is it x1 comma y1? Because we know that the point x1 y1 lies on the line x minus y equal to 4. That is the way, that is the method in which we obtained the value of y1. When the x1 remains constant, we are going along this same vertical line. So this indeed is the point x1 comma y1. We use this particular equation to get y2, now to get x2. So we will keep the same value of y1 and we will go along. So along this horizontal line the y1 value remains the same, and the point where that horizontal line intersects this particular line, that is where we will get the value of x2. So this particular point is going to be x2 comma y1. Okay. Now we keep the value of x2 the same, that means we go along the vertical line and find where this particular curve intersects the vertical line intersects this particular curve, and when we project we will essentially reach over here. This point is nothing but x2 y2. We will keep the y2 same and we will reach this point x3 comma y2, and when we project along, this point we get is x3 comma y3. We are starting from the origin and we keep going in circles, and that circle or that spiral is essentially expanding spiral. So the method that we are going to use, if x plus 2y is our first equation and x minus y equal to 4 is the second equation, we are not going to reach the desired solution, that is this particular point. Okay. Now an alternate way how we went about this is we used this particular curve to get x and we use this particular curve essentially to get y. Okay. And how that is going to go is we start at the origin. Okay. Okay. The x axis is the axis representing the curve where y0 equal to 0. So we will use this particular equation now in order to get x1. Okay. So the x1 is going to be the point where this horizontal line intersects this particular axis. So this is going to be our x1 comma y0. Okay. Now we project along this particular vertical line. The vertical line, again to remind, it represents the line at which x equal to x1, and where this intersects this line is y1. So this point becomes x1 comma y1. Okay. This becomes x2 comma y1. This point becomes x2 comma y2, and as we keep iterating we will spiral in towards the desired solution. Okay. So if we are going to use this particular curve as the curve to get x and this curve as a curve to get y, what happens is we start spiraling essentially towards the center of the intersection of these two lines. So this starts attracting essentially all the trajectories of the Gauss-Siedel iteration if we ensure that our system of equations is indeed diagonally dominant. Okay. So this is the graphical representation of how the Gauss-Seidel iterations essentially work. We have the equation Ax equal to b, and we expand that equation, we can write this as a11 x1 plus a12 x2 plus a13 x3 and so on. Okay, so we will essentially have n equations of this type. The first equation we will use in order to get, so this is, let us assume that we have gotten this equation after rearranging such that the diagonal dominance condition is met. If the diagonal dominance condition is met, then we will just go ahead and use the first equation to get x1, the second equation to get x2, and so on. So we will take all these terms on to the right hand side and divide throughout by a11. So what we get is x1 equal to b1 minus a12 x2 minus a13 x3 a1n xn divided by a11. Okay. This we can write it down as b1 minus summation j equal to 1 to n j not equal to 1 a1j xj divided by a11. Okay. This is how we have written our x1 as. Likewise we can write our x2 as b1 b2 minus summation j equal to 1 to n j not equal to 2 a 2j xj whole divided by a22, and so on we will be able to write for each of the xi's. I am sorry, generalizing for xi, or xi is going to be written as bi. Okay. Keep in mind we are following the same pattern. When we go from x1 to x2 to x3, we change from b1 to b2 to b3 and so on. So bi minus summation from j equal to 1 to n j not equal to I. Okay, j equal to 1 to n j not equal to I, a I comma j xj, a I j times xj divided by a I. Okay, this is just the diagonal term of the ith equation. This is the right hand side of the ith equation, and to the left hand side we have taken all the non diagonal terms in the ith equation. Okay, and then we will go ahead and solve this equation in order to get a1, a2, a3 up to an, and we will keep repeating this until we get the desired convergence. This equation of course we can also will be able to write it as bi minus summation of j equal to 1 to I minus 1 a ij xj minus summation j equal to I plus 1 to n a ij xj divided by a I. That is going to be our xi. What we will use to get xi value is all the old values for xi in the subdiagonal elements and all the new values of xi in the super diagonal elements. So xi from the at the iteration value n, we are going to get that equal to bi aij xj n minus aij xj n minus 1 represents the Gauss-Siedel method. Okay. So the steps that we take in Gauss-Siedel method is first to see if the equations can be put in diagonally dominant form. Once the equations are put in the diagonally dominant form, decide on initial values of x0, y0 and so on and so forth for all the variables, and then run this iteration step using this equation for I equal to 1 to all the values of x that we have, and we keep doing this iteration multiple times so that we get the solution to converge to the predefined tolerance value. Okay. So this is the Gauss-Siedel method. Okay. In Gauss iteration, we just keep the latest values of x1, x2 up to xn. In the Jacobi iteration, we do not keep only the latest value, we also keep the previous value, and we iterate based on only the previous values of x and not the most current values of x. So the equation that we had for Gauss-Siedel, we will just change it. So we have xi equal to bi minus summation I equal to 1 to n minus 1 j I equal to j to n minus 1 a ij xj minus summation j equal to I plus 1 to n okay. And what we had in Gauss-Siedel iteration is this had an index n, whereas this had an index n minus 1. The difference between Gauss-Siedel iteration and the Jacobi iteration is both of them have the index n minus 1, which basically means that we are not going to use the latest values for the previous variables, but we are going to use the values from the previous iteration. Okay. Or a more compact way of writing this is bi minus summation j equal to 1 j not equal to I up to n a I j x j okay. This should be I minus 1, not n minus 1. Okay. And this essentially is the Jacobi iteration. Okay. And to go back to the previous example of x minus y equal to 4 and x plus 2y equal to 1, we will write those equations as x okay. So what we did was we started with x0 equal to 0, y0 equal to 0, we substitute the value of y0 over here and get x1 4. What we did in Gauss-Siedel method is then substitute this value of 4 in this equation, and we got 1 minus 4 divided by 2 equal to minus 1.5. But what we do in the Jacobi iteration is instead use the x0 and y0 values itself in these equations. So we do not use the latest value, we use actually the previous value x0 in this equation, so that y1 we are going to get equal to 0.5. Now we substitute the value of 0.5 in this equation to get the value of x, we substitute the value of 4 in this particular equation to get the value of y. Okay. So our x2 we will get it as 4.5, our y2 that we will get is essentially going to be 1 minus 4, that is minus 3 divided by 2, and that is minus 1.5. Okay, and we keep repeating this process over and over again until we reach convergence. What we will see actually is that the conditions for convergence of Gauss-Seidel method as well as for the Jacobi iteration method remains the same, only the procedure in which we do the Gauss-Seidel method versus the procedure in which we do the Jacobi iterations are differ from each other in their details. Okay. So that is about the Gauss-Seidel iteration and the Jacobi iteration. Now let us take our Microsoft Excel and we will use Microsoft Excel to solve the 2 equation and 2 unknowns problem using the Gauss-Seidel method. What I will do first is I will use the Gauss-Seidel method in the form that we have the original equations in, that means equation number 1 I will use it to obtain the value of x1, and equation number 2 I will use it to obtain value of x2. As we have said, there was nothing special about calling this particular equation as equation 1 and this equation as equation 2. So what we have done is we have interchanged these 2 equations, and even after interchanging these equations what we will end up with is the same point is going to be the point of intersection of the 2 lines. And what we will do in both these methods is that we will start these methods from the origin. So initial guess is x1 is going to be equal to 0, x2 is going to be equal to 0. Okay. So because it is a Gauss-Seidel method, what we do at the second iteration, our x1 value is going to be equal to 2 minus 2 multiplied by the x2 value from the previous iteration. That is how we do the Gauss-Seidel method, because in the Gauss-Seidel method the newest values are essentially going to be used in order to compute the next value of x1 or x2. Okay. And x2, for x2 what we will do is x2 is going to be equal to 7 minus 2 times x1. Okay. In case of a Jacobi iteration, we will always use the previous iterant value in order to compute the new value. However, in the Gauss-Seidel method we will use the newest value. So x1, the previous value was 0, but in the second iteration we have replaced the value of 0 with the value of 2. Okay. So that is the value that we are going to use, and this whole thing is going to be divided by 3, and that is going to be our new guess, sorry, the new solution value that we will get from this particular equation. Okay. And we can then keep continuing this downwards, and this, and let us continue this for 10 iterations. So, this should be iteration 1, this one initial is the 0th iteration. So, this should be iteration 1 and 2. I will just drag this. See, what I have done is really clicked on the right edge and then just dragging it down, and we have 10 iterations. Okay. And at each time what we also need to do is compute the relative error. Okay. And the relative error is going to be nothing but the absolute value of the difference between the current and the previous value divided by the current value. Okay. And this is the error in okay. So that is the error in x1, and likewise we will have error in x2 as well. Okay. And for error in x2 we are just going to drag this to the left hand side. Okay. So this is the error in x1, this is the error in x2. We will click on F2 and just confirm that okay, this is what it ought to be, and we will just drag this and see how the error is changing. And when the error actually becomes less than a predefined tolerance value, that is the time when we stop our iteration. Okay. So, what happens over here is that the error does not keep decreasing with the number of iterations, and what we are actually seeing over here is that the one of the values x1 is going very negative, whereas x2 is becoming a very large positive value. So, clearly what we see is that the solution is diverging. This is what we expected based on the analysis that we had done earlier. We will do is we will use the two equations, but the 2x1 plus 3x2 equation, we are calling this as equation 1, and what was equation number 1 previously, we are calling this as equation number 2. Okay. And we will again have initial values as 0, we will start from the same initial values. Okay. And we will indeed continue in a very similar manner as before. And error. Okay. However, we will not be using the same expression as before, instead we will be using 7 minus 3 times x2 divided by 2 as a means to calculate x1, format cells subscript. Again, this is in order to avoid confusion. Okay. And if our x2 is going to be equal to 4 minus x1, and again the x1 is going to be the new value x1 divided by 2. Okay. So, this so from 0 our x1 value has gone to 3.5, from 0 our x2 value has gone to 0.25. We will just select this and drag it to see where these solutions are leading us. Okay. If we recall, our solutions were 2, 1, so we are getting closer and closer to the solution, and we will need a few more iterations in order to reduce the error to the level that we desire. Okay, we need 10 to the power minus 3 at least as the accuracy. So, let us go and do this a little bit more. Maybe I will just expand these cells a little bit further. Okay, so our accuracy is not yet met. We are looking for our the error epsilons to go below a tolerance value of 10 to the power minus 3. That is when we will stop our iterations. Okay, this is when the solution, the error value has gone below 10 to the power minus 3, and this is what we will take as an approximate solution from the iterative method. Okay. So, to recap what we have done so far, we took two equations in two unknowns, we wrote them down in this particular form as well as in this form. The difference over here is that the equation 1 in this case is taken as equation number 2 in this case, equation 2 in the first case is taken as equation number 1 in this particular case. What we saw is that when in the first example the diagonal dominance condition was not met, as a result our solution diverged, whereas in the second example the diagonal dominance condition was met, and what happens is that we indeed finally reach the desired solution. Okay, the solution is accurate to the accuracy that we have asked our solver. If we say we need a greater accuracy, we need to go ahead and do a few more iterations, and I can show you the results. Okay. And if let us say we were to ask for an accuracy of 10 to the power minus 4, this is the solution that we will get. And let us see the number of iterations that are required. So, this is the initial guess, so that is the 0th iteration, this is the first iteration. okay, and I will just drag this. Okay, and we require 29 iterations if the error tolerance is 10 to the power minus 4, and if the error tolerance is 10 to the power minus 3, we require 21 iterations. And just the way we did for the Gauss-Siedel method, we will do we will solve the Jacobi method in a similar manner. I will change the font size. Okay. Okay. So, we have iteration number x1 and x2 we will compute in the same manner. And then errors again we will compute in the same manner. Okay, so what I am going to do is I will go back and copy paste this rather than having to redo it myself again, because nothing really changes over here. Okay, and I am getting this hash signs because the error I am defining as the difference between the two divided by this particular value, and this value because no value is specified over here is taken as 0. So, this is equation 0 divided by 0, as a result of which we get hashes. As soon as we populate these results, we will not get hashes and it will be replaced by the appropriate numbers over there. Okay, so we will have number of iterations. Okay, and I will just drag to say 15 iterations, and we start with x1 equal to 0 and x2 equal to 0. Okay, x1 the way we calculate does not change because x1 is the newest value all the time. So, the calculation of x1 does not change, the calculation of x2 is going to change. So, I will copy paste it and then show you how we change the way we compute x2 using the Jacobi iteration. Okay. So, this is the pasted value is for the Gauss-Siedel method, it is not for the Jacobi method. Okay. So, in Gauss-Siedel method we have 4 minus the latest value of x1 divided by 2. This is not how the Jacobi iteration works. In Jacobi iteration we do not use any of the values in this particular row, we will use only the values in the upper row. So, what I will do is I will just take this particular cell, look where my cursor is at edge of the cell, it changes from a plus sign like a white cross type of a sign to a cross arrows type of a sign over here. When it changes to this type of an arrow, this type of a sign, the cursor, I will click the left key, with the left mouse key depressed, that particular plus arrow sign has disappeared. Now, I can move this anywhere. So, as I move this my mouse along, you can see this blue color square moving, and as the blue color square is moving, this particular formula is changing. So, I will move this blue color square from the new value of x1 to the old value of x1, and that should give me the Jacobi iteration. Okay, and I will click enter, and this is the result from the Jacobi iteration. Okay, so, to recap, what we do in Gauss-Siedel method is we use only the latest value. In Jacobi iteration we use only the values from the previous iteration and not the latest value. So, in this particular case the value from previous iteration are 0 and 0. As a result, for the Jacobi iteration we compute 4 minus m4 4 minus m6 and not 4 minus m7 as was done in the Gauss-Siedel method. Okay. We will just highlight this entire row and drag it for 15 iterations and see what we are getting. Okay. In 15 iterations our solution has not yet converged. Let us go to say 40 iterations as before. Okay. And I will select this particular row, and instead of dragging the row downwards, if the row adjoins another row which the column adjoins another column which is full, we can actually just double click at the right end and the Excel will fill itself. Okay, so I have double clicked over here and Excel has filled the values, and we want our overall error to be 10 to the power minus 3 at least. So we need to drag this a little bit further. Okay, we have still not reached, yes. So finally after 54 iterations we have reached the solution. Okay, whereas in the Gauss-Siedel method we have reached the solution in only 21 iterations. The reason why this happens in the Gauss-Siedel method against the Jacobi method is because the Gauss-Siedel method uses the latest values of the variables, whereas the Jacobi iteration uses the previous iterant values of the variables. Okay. However, both these methods have linear rate of convergence. So although in this particular example we were able to see such a big difference in the number of iterations required for the Jacobi iteration to converge compared to the Gauss-Siedel iteration, in general the experience has been that the Jacobi iteration is able to converge fairly rapidly, I mean as rapidly as a typical Gauss-Siedel iteration. In general I find that using a Gauss-Siedel method to be a more preferred method, and the reason for this is that when we are solving this overall equation by the Gauss-Siedel method, we only need to keep in n number of values when we have n variables. So every time we recompute the variable we do not need to store the previous value. Okay. So what we have done in today's lecture, the lecture 6 of module 3, is to look at the iterative methods for solving a linear equation A of the type Ax equal to b, and now what I will do is use the next few minutes to summarize what we have done in this module. In this particular module, that is module 3, we have primarily covered computational methods for solving linear equations of the type Ax equal to b. The first thing that we started off with was Cramer's rule. Cramer's rule involves finding determinants, and finding determinants is extremely computationally complex. As a result, Cramer's rule is not used beyond say the 4 or 5 dimensional systems. Okay. Using this Cramer's rule idea, we motivated a few things further. We said that if rank of the matrix A in Ax equal to b is equal to n, where n is the size of the vector x, okay, then we will get a unique solution. Okay. If rank of the matrix is not equal to n, if the rank of matrix A is less than n, then we need to check the rank of matrix AB and the rank of matrix A. If both these ranks are equal, then we have infinite number of solution. If rank of this guy is greater than rank of A, it is going to be no solution. Okay, and then we gave a geometric interpretation of this also in terms of vector spaces. Next we covered the direct methods. The first method that we covered very extensively was the Gauss elimination method. The idea of Gauss elimination is to use row operations to convert in the matrix A into an upper triangular form. What we also saw in the previous lecture of this module is that the computational effort required in Gauss elimination is of the order of n cubed. Okay. The next method we talked about was a Gauss-Jordan method. In Gauss-Jordan method we use row operations to convert the matrix A not into a upper triangular matrix but into an identity matrix, and whatever is left of the matrix B in the juxtaposed matrix AB is going to be the solution X. We then also talked about the LU decomposition method. The first part of LU decomposition is exactly the same as Gauss elimination. We use Gauss elimination to get the upper triangular matrix, and all the coefficients that are used in each pivot row are going to actually form the lower triangular matrix in the LU decomposition method. Then towards the end of the lecture 5 in this module we covered sparse matrices. Specifically we covered tri-diagonal matrix, and to solve the tri-diagonal matrix we covered an algorithm called the Thomas algorithm or the tri-diagonal matrix algorithm. The Thomas algorithm is similar to Gauss elimination, but it exploits the special structure of the sparse matrix, because of which the overall effort required in computing solution using Thomas algorithm is of the order of n to the power 1 rather than it being of the order of n to the power 3. Okay. So, that was what we discussed about the Thomas algorithm or the TDMA. And finally, in this particular lecture we covered iterative methods and the geometric interpretation of the iterative methods. The first iterative method we covered was the Gauss-Siedel method, and this was the overall expression for Gauss-Siedel method. What we did was, for each equation we took all the elements from the left hand side over to the right hand side and used whatever is left as an iterative equation. So, we started with some initial guess of x values and we kept improving the guess by iterating it over this particular equation. This is an equation we saw a few moments ago. In Gauss-Siedel we use the most recent values of x, that means for computing xi we use the m plus 1th values of x1 up to xi minus 1, and we use the mth value from xi plus 1 up to n, because we do not have the m plus 1th values of xj at this point. Okay. So, we use the latest value in computing xi in Gauss-Siedel method, whereas in Jacobi iteration method we do not use the latest value, but we use the values from the previous iteration. And the change between Gauss-Siedel and the Jacobi iteration I have just highlighted over here. In Gauss-Siedel we got m plus 1 as the iteration number over here, whereas in Jacobi iteration we get this iteration number m at itself. Okay. So, these were the two main classes of methods, the direct methods and the iterative methods when solving the linear algebra. Okay. So, with that we come to an end to module 6, with that we come to an end to module 3, and from next lecture onwards we will start with module 4, which will cover solving non-linear algebraic equations.